So alcohols can also be acids. And assuming we're using water, we get an equilibrium like this, and this is kind of the standard thing you've seen a million times. Gen Chem, we use this equilibrium to measure acidity, which we represent with the pKa value. So you've seen this before, and I'm just going to quickly show the logic again. So if you have acid plus water, you have A minus plus H3O, K equilibrium is products over reactants. That's the equilibrium equation. If we assume that the concentration of water is constant, then this becomes a simpler equation. We just kind of factor it out. K then Ka is the same equation minus the water in there. And with pKa is negative log 10 of that. So pKa is ultimately a measure of dissociation, and it's the universal measure of acidity in organic chemistry, right? So, smaller pKa equals strong acid or weak acid? Strong acid. Large pKa is a weak acid, right? Okay, so a couple of examples. I think as table 17.1 has some pKa values of various alcohols. That's useful. pKa of alcohols and phenols. But let's just do a couple of them ourselves real quick. Actually, yeah, let's draw a couple. Okay, so T-butanol is a little less acidic than most alcohols. Ethanol is kind of the baseline at 16, which is about the same as water. Trifluoroethyl. So trifluoroethanol is 12. That's interesting. So when you have the trifluoromethyl group on that molecule drops the pKa a little bit. Phenol, even more acidic, 9.89. So we have several effects that kind of modulate the pKa values. Let's talk about them. All right, so first one. Methanol versus tert-butanol. This is about 16. This is about 18. So why is methanol more acidic? About 100 times more acidic in logarithmic terms. Why is methanol more acidic? Any ideas? Usually the first answer anybody says is, oh, sterics. The terbutanol is more sterically hindered, but that has nothing to do with acidity directly. And so what do you consider when you're trying to explain acidity of a molecule, relative acidity? Conjugate base, stability of the conjugate base. Okay, that's pretty much the universal explanation for acidity in organic chemistry. Is some kind of stability or stabilization of the conjugate base. Right. So stability of conjugate base. So in one case we have that's our conjugate base for methanol. And that's our conjugate base for terbutanol. Okay, so the idea is negative charges are a little unstable. Okay, and methanol can be blanketed around solvents. I'm just going to say S. S for solvent. Okay, tons of solvents hanging around that conjugate base. Okay, tons of solvent. Now the problem here is can't do it as much because actually that steric argument is reasonable. Those three methyls around there kind of block solvation. So there's less of it. Less stabilization due to solvent. Okay, that's it. In one case, we have more stabilization, and in the other case, we have less stabilization. And that is reflected in acidity. One's more acidic, one's less acidic. So more stabilization. So that's how we explain methanol versus terbutanol, right? Okay, so now this is 16, 12.4, I think we said. All right, so terbutanol is a little more acidic. Why? Yeah.
But wouldn't, like, if we have different solvents for like the two molecules,
Yeah.
it could be that the more stable is the methyl, like the methyl hydroxide. Right.
That's
If
true,
it's-
but the
it's a polar
point is we're
versus-
trying to explain acidity. We're trying to, and acidity is ultimately stabilization of the conjugate base. So everything's kind of based on stabilization of the conjugate base. If the point is to explain acidity, yeah, and everything else is the same. Yeah.
Does methanol ever form like a resonance structure?
Nope. No resonance structures. You need pi bonds. There's no pi bonds. Yeah. You need double bonds to do resonance. No resonance issues there at all. Can't do resonance without breaking a sigma bond. You can't do that. Okay. All right. So again, in this example, you do the same thing. You have to go to the conjugate bases. All right. So let's do ethoxide versus trichloroethoxide. And who's more stable? The one on the right. And it's that inductive effect. So there's an inductive stabilization. The fluorines kind of withdraw the electron density through the molecule, through the sigma bonding. So there's inductive stabilization. Yep. Inductive stabilization. So in this molecule, the conjugate base has inductive stabilization in which case the electrons are transmitted through the molecule towards the fluorines. It's not a resonance effect, right? Resonance requires high electrons. We don't have that. So it's transmitted through the sigma bonding network, and the electrons are delocalized. When the electrons are delocalized, that's usually a stabilizing effect. The electrons are kind of spread out, and that's a stabilizing thing. And what does that reflect? What does that do? It explains why it's a little more acidic. Trifluoroethanol is a little more acidic because its conjugate base has some extra stabilization. Can this do that? No. It doesn't have the fluorines. The fluorines do something. The fluorines help delocalize electrons, right? So that's explanation. Last one. This is an easy one. Okay, so this one, simple alcoholic ethanol, which is phenol. Phenol is significantly more acidic, like almost a millionfold. Actually, yeah, more than a millionfold more acidic because it's logarithmic. So what you do now is consider the conjugate base. Universal explanation. Think about the conjugate base. And of course, now we have something else. Everybody knows this one inside and out. Resonance stabilization of the conjugate base. Extensive. Phenoxide. So that thing is called phenoxide. This thing is called phenol. But when you take the proton off, it's called phenoxide. And of course, there's extensive resonance stabilization, right? You can do this one yourself, of course. Et cetera, et cetera, et cetera. So you can push the electrons around the ring. And that's why it's a million times more acidic, is because you have extensive resonance stabilization. All right. Next time we're jumping into reactions and mechanisms and all that fun stuff. Wait, and all waiting.